Welcome to this session. In this session, we are going to use the discontinuous method to determine the concentrations of sodium carbonate and sodium hydroxide in a mixture. Let's look at the objective for the session. At the end of the session, you should be able to determine the concentrations of sodium carbonate and sodium hydroxide in a mixture using the discontinuous. And here is the problem to solve. F is an aqueous solution of sodium triazocarbonate 4 contaminated with the sodium hydroxide. So it's a mixture of sodium carbonate and then sodium hydroxide. G is 0.1 molar HCl. Put G into the burette and form the following: pipette 25 cubic centimeters of F and titrate against G using phenolphthalein indicator. Then pipette another 25 cubic centimeters of F and titrate it against G using methyl orange as indicator. Then we repeat these exercises. So from here we can tell that it is a discontinuous method. We are to write the equations at the phenolphthalein endpoint and the methyl orange endpoint, and then find the amount concentrations of sodium carbonate and sodium hydroxide, as well as the percentage composition of each of sodium carbonate and sodium hydroxide in the sample used in preparing F. We've been given the volumes of G at the various endpoints. At the phenolphthalein endpoint, we have been given 15, and at the methyl orange endpoint, we've been given 25. Okay, so let's solve the problem. We are to write the equations to show the reactions at the two endpoints. At the phenolphthalein endpoint, this sodium hydroxide is a strong base. We expect a complete neutralization, and so that produces the salt and the water. So we have NaOH plus HCl giving us sodium chloride and water. Now with the sodium carbonate, it is only half of it that is going to be consumed or that is going to react, and in that case we are going to have sodium hydrogen carbonate or the sodium bicarbonate and the salt. This is the point, or this is where the phenolphthalein is going to change, or the phenolphthalein changes color. It is not going to wait for the whole of this to react before it changes color. Now at the methyl orange endpoint, we expect everything to react. So sodium hydroxide will fully react, so we have this equation to show. The sodium carbonate to it will all react, and we have this equation also to show. But before we proceed, we should let the volume of acid at phenolphthalein endpoint be represented by V1, and that at the methyl orange endpoint represented by V2. But let's look at what is happening at the phenolphthalein endpoint. Remember, in the equation we said the whole of sodium hydroxide will be neutralized, whilst half of the sodium carbonate will react. So the volume of the acid that was used, in other words, the volume that was read from the burette, was the volume of the acid that converted the whole of the sodium hydroxide and half of the sodium carbonate. Let's leave this one as our equation 1, because there is nothing more we can do to this. We need data from the second endpoint. At the methyl orange endpoint, what is happening here? We said that at this endpoint, we are going to have the whole of the sodium hydroxide being consumed, the whole of the sodium carbonate being consumed. So the volume of the acid is the volume that did that job. From here we can do some mathematics. Okay, we can subtract equation 1 from equation 2, and if we are subtracting, this sodium hydroxide will cancel this sodium hydroxide. This is a full sodium carbonate and this is half of it. So if we take this half from this full, we'll be left with half of the sodium carbonate, which is this. And then at the other side too, we are still going to do the subtraction. It was we subtracted 1 from 2, so this is the 2, which is V2, and we are taking V1 from it. So that's why we have this one also here. Which means that, so we have half of the sodium carbonate going into V2 minus V1. So letting sodium carbonate stand alone, we are going to have 2 times V2 minus V1. Let's put in the values. V2 is given as 25, V1 is given as 50. So 2 times the difference gives us 20 cubic centimeters. So this is the volume of the acid that reacted or that consumed the sodium carbonate completely. So we can now find the number of moles in this 20 cubic centimeters of the acid, and we'll do our mole ratio. So in doing that, we could have just converted the 20 cubic centimeters into decimeters cubed and multiplied by the concentration to get the moles. But we are going by the first principle, and so we interpret the concentration as if 1000 cubic centimeters contains 0.1 mole, then the 20 cubic centimeters will contain what? So when we work this out, we have this number of moles. Now this is the moles of the acid that reacted with the sodium carbonate. So we need an equation of reaction to show the reaction that took place. Then we do our mole ratio. So from this equation, 2 moles of HCl reacted with 1 mole of the sodium carbonate. So if 2 is equal to 1, then 0.002 is equal to what? That will give us 1 over 2 times 0.002 moles of the sodium carbonate. So the moles of the sodium carbonate is 0.001 mole. This is the moles of the sodium carbonate contained in that 25 cubic centimeters that was pipetted. So we have to take it into 1000, and we say if 25 contains 0.001, then 1000 is equal to what? We work this out and our answer is 0.004 moles per cubic decimeters of the sodium carbonate. Okay, so let's look at that of the sodium hydroxide also. And with that too, we are going to need the volume of the acid that completely neutralized it. We left an equation on the way. Alright. At the metal orange endpoint, we said that it was the volume of the acid used was the volume that converted the whole of the sodium hydroxide and the whole of the sodium carbonate. We have been able to find the volume of acid that reacted with the whole of the sodium carbonate, and that we had the relation Na2CO3 is equal to 2 times Va2 minus Va1. Okay, so we just have to put this in place of the sodium carbonate in this relation. So when we put it there, then we have NaOH plus 2 times V2 minus V1 is equal to V2. So we work this out, and finally we have NaOH being equal to 2V1 minus V2 cubic centimeters of the acid. So let's put in our values, that of V1 and that of V2. It gives us 5 cubic centimeters. So this is the volume of the acid that reacted completely with the base. We need to find the number of moles in this 5 cubic centimeters so that we can do our mole ratio. And from the concentration, we interpret as 1000 being equal to 0.2 moles. If 1000 is equal to 0.2 moles, then this 5 cubic centimeters will contain how many moles? It will contain 0.0005 moles. We go to the equation of reaction to find the agreement between them. So from this equation, the mole ratio is 1:1. If that's the case, then the moles of sodium hydroxide is also equal to 0.0005 mole. So this is the moles of the sodium hydroxide in the pipette volume, which was 25. So if 25 cubic centimeters of sodium hydroxide contains 0.0005 moles, then 1000 will contain what? It will contain 0.02 mole per cubic decimeters of sodium hydroxide. So this is the amount concentration. Okay, we were to find the mass concentrations, and using the relation mass concentration is equal to amount concentration times molar mass, we do substitution. The concentration of sodium carbonate, we found it to be 0.04, and the molar mass from the atomic masses is 106 grams per mole. So when we do this multiplication, we have 4.24 grams per cubic decimeters. With that of the sodium hydroxide, we are going to do the same thing. The amount concentration is what we have found here to be 0.2, and the molar mass of sodium hydroxide is 40 grams per mole, and this multiplication also gives us 0.8 grams per cubic decimeters. We have to find the total. We have to find the percentage composition, but to do that, we will need the total mass so that we can work it out. The total mass is the mass of the sodium carbonate and or plus that of the sodium hydroxide, and we have 5.04. So this becomes our total. To know the percentage of each, we just have to divide its mass by the total mass and multiply by 100. So that of the sodium carbonate will be 4.24 divided by the 5.04 times 100. It gives us 84.1. And the sodium hydroxide is going to be its mass, which is 0.8, divided by the total mass, 5.04 times 100. And that also gives us 15.9. My good friends, I hope you enjoyed this session very well. We'll meet again in the next session.